topic of today's module is class of rings. Dear learners, in this session we are going to learn about commutative ring, non-commutative ring, integral domain and fields. Commutative rings. In ring theory, a branch of abstract algebra, a commutative ring is a ring in which the multiplication operation is commutative. The study of commutative rings is called commutative algebra. We recall the definition of a ring. A ring R is a set equipped with two binary operations, that is operations that combine any two elements of the ring to a third. They are called addition and multiplication and commonly denoted by plus and dot. For example, A plus B and A dot B. To form a ring, these two operations have to satisfy a number of properties. The ring has to be an abelian group under addition as well as a monoid under multiplication, such that multiplication distributes over addition. That is, A dot B plus C equal to A dot B plus A dot C. The identity elements for addition and multiplication are denoted 0 and 1 respectively. Let us see the definition of a commutative ring. If R satisfies the commutative property, that is A dot B equal to B dot A, then the ring R is called commutative. A commutative ring which has an identity element is called commutative ring with identity. Let us see some example of commutative rings. The first example is, consider the set of integers is set with operation usual addition and multiplication. We already proved that the set of integers is set with the usual operation addition and multiplication forms a ring. Now we want to show that commutative property. Let A and B in is set. Then clearly AB equal to BA. Therefore, Z plus dot is a commutative ring. The second example is, consider the set of all complex numbers C under complex addition plus and multiplication. We already proved that the set of complex numbers C with the usual operation addition and multiplication forms a ring. Now we want to show that the commutative property. Let A plus IB and C plus ID are in C. Then A plus IB into C plus ID equal to AC plus IAD plus IBC minus BD, and C plus ID into A plus IB equal to CA plus ICB plus IDA minus DB, that is equal to AC plus IBC plus IAD minus BD. From the above, A plus IB into C plus ID equal to C plus ID into A plus IB. The C plus dot is a commutative ring. Some other commutative rings are, the set Zn equal to set of all 0, 1, etc. up to n minus 1 under addition and multiplication modulo n is a commutative ring with unity 1. The set of units is U of n. The set 2 is set of even integers under ordinary addition and multiplication is a commutative ring without unity. The set of real numbers R under ordinary addition and multiplication is a commutative ring with unity 1. The set of rational numbers Q under ordinary addition and multiplication is a commutative ring with unity 1. Special classes of commutative rings are integral domain, unique factorization domains, principal ideal domains, Euclidean domains and fields. Let us see the definition of integral domain. An integral domain is a commutative ring with unity and no zero divisors. The examples of integral domains are the ring Z of x of polynomials with the integer coefficients is an integral domain. The ring of Gaussian integers Z of I equal to set of all a plus ib such that a comma b belongs to Z is an integral domain. The ring Z of root 2 equal to a plus b root 2 such that a comma b belongs to Z is an integral domain. The ring Zp of integers modulo a prime p is an integral domain. The ring Zn of integers modulo n is not an integral domain when n is not prime. One of the example for non-integral domain is Z6 under addition modulo and multiplication modulo, because the modulo product of two non-zero elements 2 and 6 is 0. Next is the definition of unique factorization domain. An integral domain R is a unique factorization domain if the following conditions hold for each element A of R, that is neither 0 nor a unit. A can be written as the product of a finite number of irreducible elements of R. This can be done in an essentially unique way. If A equal to P1, P2, etc. Pr and A equal to Q1, Q2, etc. Qs are two expressions for A as a product of irreducible elements, then S equal to R and Q1, Q2, etc. Qs can be reordered so that for each I, Qi is an associate of Pi. The examples of unique factorization domains are Z is a unique factorization domain. The Gaussian integers Z of I equal to set of all a plus bi such that a comma b belongs to Z is unique factorization domain. Next one is the definition of principal ideal domains. A principal ideal domain is an integral domain in which every proper ideal can be generated by a single element. The examples of principal ideal domains are the integers Z, the Gaussian integers Z of I equal to set of all a plus bi such that a comma b belongs to Z, and the set of polynomials in one variable with real coefficients. Definition of Euclidean domains. An integral domain R is called a Euclidean domain if there exists a function f from R to positive integers such that for a comma b not equal to 0 in R, f of a b greater than or equal to f of a. If a comma b belongs to R and b not equal to 0, then we can write a equal to bq plus r with q comma r belongs to R such that either r equal to 0 or f of r less than f of b. The examples of Euclidean domains are Z is a Euclidean domain with f of a equal to cardinality of a. The ring Z of I equal to set of all a plus bi such that a comma b belongs to Z is a Euclidean domain. In the later modules, we will give more details about the unique factorization domains, principal ideal domains and Euclidean domains. Let us see the definition of field. A field is a commutative ring with unity in which every non-zero element is a unit. That is, every non-zero element has a multiplicative inverse, which means every non-zero element has inverse with respect to the second operation dot. And the example is R, Q and C are fields. Zn is a field if and only if n is a prime. We already know that Zn is a commutative ring with unity. If n is non-zero prime, then n has a divisor say k. So, k dot q equal to 0 for some q in Zn. Therefore, k is not a unit. If n is prime, then clearly every non-zero element has a multiplicative inverse. Some specific kinds of commutative rings are given with the following chain of class inclusions. Set of all commutative rings is a superset of set of all integral domains is also a superset of set of all unique factorization domains is a superset of set of all principal ideal domains is a superset of set of all Euclidean domains, which is also a superset of all fields. Properties of commutative rings. Here let us see some properties of commutative rings as a result. The first result is a ring R is called a Boolean ring if A square equal to A for all A belongs to R. Prove that every Boolean ring is commutative. Proof is, assume R is a Boolean ring so that A square equal to A for every A belongs to R. Let B and C belongs to R. We will show BC equal to CB. First, we note that B plus C equal to B plus C the whole square, that is equal to B plus C into B plus C, that is equal to B into B plus C into B plus C, that is equal to B square plus BC plus CB plus C square, that is equal to B plus BC plus CB plus C, since R is Boolean. By cancelling B plus C from both sides, we are left with 0 equal to BC plus CB, hence minus BC equal to CB. However, for every A belongs to R, we have minus A equal to minus A square, since R is Boolean. So, we replace A by BC, we get minus BC equal to minus BC the whole square, that is equal to minus BC into minus BC, that is equal to minus BC into minus BC, that is equal to minus of BC the whole square, that is equal to BC the whole square equal to BC, since R is Boolean. Therefore, from minus BC equal to CB, we get BC equal to CB. Let us see some results. The first result is, let R be a ring and assume that whenever AB equal to CA, for some elements A, B, C belongs to R, we have B equal to C. Then prove that R is a commutative ring. Proof is, let x comma y is an arbitrary elements in R. We want to show that xy equal to yx. Now consider the identity y into xy equal to yx into y. This can be written as AB equal to CA if we put A equal to y, B equal to xy and C equal to yx. It follows from the assumption that we have B equal to C. Equivalently, we have xy equal to yx. As this is true for any xy belongs to R, we conclude that R is a commutative ring. The second result is, let R be a ring with unit 1. Suppose that the order of R is order of R equal to P square for some prime number P. Then prove that R is a commutative ring. Proof is, let us consider the subset Z equal to set of all Z belongs to R such that ZR equal to RZ for any R belongs to R. This is called the center of the ring R. This is a subgroup of the additive group R. In fact, if Z and Z dash belongs to Z, then we have for any R belongs to R, Z minus Z dash into R equal to ZR minus Z dash R, that is equal to Rz minus Rz dash, that is equal to R into Z minus Z dash. It follows that Z minus Z dash belongs to Z and thus Z is a subgroup of R. Note that 0 and 1 belongs to Z, hence Z is not a trivial subgroup. Thus, we have cardinality of Z is either P or P square, since R is a group of order P square. If cardinality of Z equal to P square, then we have Z equal to R. By definition of Z, this implies that R is commutative. It remains to show that cardinality of Z not equal to P. Assume that cardinality of Z equal to P. Then R by Z is a cyclic group of order P. Let alpha be a generator of R by Z. Since Z not equal to R, there exists R comma S belongs to R such that R is not equal to SR. We write R equal to M alpha plus Z and S equal to N alpha plus Z dash for some M comma N belongs to Z and Z dash belongs to Z. Then we have R is equal to M alpha plus Z into N alpha plus Z dash, that is equal to M alpha into N alpha plus M alpha Z dash plus Z N alpha plus Z dash. Since Z and Z dash are in the center, we write M alpha into Z dash as Z dash into M alpha and Z into N alpha as N alpha into Z. Thus, we get N alpha into M alpha plus Z dash M alpha plus N into alpha Z plus Z dash Z. By taking N alpha common from first and third term and Z dash from second and fourth term, we get N alpha into M alpha plus Z plus Z dash into M alpha plus Z, that is equal to N alpha plus Z dash into M alpha plus Z, that is equal to SR. This contradicts R is not equal to SR and we conclude that order of Z not equal to P. Non-commutative rings. A non-commutative ring is a ring whose multiplication is not commutative. That is, if R is a non-commutative ring, then there exists two elements A and B in R with A dot B not equal to B dot A. Non-commutative rings are ubiquitous in mathematics and occur in numerous senses. For instance, matrix multiplication is never commutative except in trivial cases, despite the fact that matrices arise naturally as rings of linear transformations of some vector space over a field. Furthermore, mathematical physics exploits the concept of a matrix and more generally linear algebra often. Non-commutative rings also arise naturally in the representation theory of groups. Algebras and more specifically group algebras occur also in non-commutative ring theory. The study of non-commutative rings is a major area of modern algebra. Basic influential concepts in the field include the Jacobson radical, the Jacobson density theorem, the Artin-Wedderburn theorems and the Brouwer group. Let us see the definition of non-commutative ring. First, see the definition. A non-commutative ring R is a ring in which the law of multiplicative commutativity is not satisfied. That is, A dot B not equal to B dot A for some A and B in R. In such a case, the elements A and B of the ring R are said not to commute. An important example of a non-commutative ring is the ring Mn of F consisting of all n by n matrices whose elements are members of the field F. The following examples will give more clarification towards the non-commutative rings. Let us see the examples. The 2 by 2 matrices with entries in R form a ring under the usual operations of matrix addition and multiplication. This ring is non-commutative since it is usually the case that AB not equal to BA. Also notice that we can have AB equal to 0 when neither A nor B is 0. For instance, the matrix product of the matrices 1 0 0 0 and 0 0 1 0 is the 0 matrix, that is AB not equal to BA. Consider a field F and an integer n greater than or equal to 2. The set Mn of F of square matrices over the field F is a ring. Mn of F is not commutative. Indeed, for given matrices A equal to 0 1 1 0 and B equal to 0 1 0 0, we have AB equal to 0 0 0 1 not equal to 1 0 0 0 equal to BA. Therefore, with matrix rings, we get examples of non-commutative rings that can be finite or infinite depending on whether F is finite or not. One can notice that Mn of F is never a division ring as B square equal to 0. Consequently, B cannot have a multiplicative inverse. Show that the ring of quaternions is non-commutative. Let 1 equal to 1 0 0 1 and I equal to 0 1 minus 1 0, j equal to 0 I 0, k equal to I 0 0 minus I, where I square equal to minus 1. These elements satisfy the following relations: I square equal to j square equal to k square equal to minus 1, ij equal to k, jk equal to I and ki equal to j, ji equal to minus k, kj equal to minus I, ik equal to minus j. Let H consist of elements of the form a plus bi plus ej plus dk, where a, b, c and d are real numbers. We can define addition and multiplication on H either by the usual matrix operations or in terms of the generators 1, I, j and k. A1 plus B1i plus C1j plus D1k plus A2 plus B2i plus C2j plus D2k equal to A1 plus A2 plus B1 plus B2 into I plus C1 plus C2 into j plus D1 plus D2 into k, and A1 plus B1i plus C1j plus D1k into A2 plus B2i plus C2j plus D2k equal to alpha plus beta I plus gamma j plus delta k, where alpha equal to A1 A2 minus B1 B2 minus C1 C2 minus D1 D2, beta equal to A1 B2 plus A2 B1 plus C1 D2 minus D1 C2, gamma equal to A1 C2 plus B1 C2 minus C1 B2 plus D1 A2, and delta equal to A1 D2 plus B1 C2 minus C1 B2 plus D1 A2. Though multiplication looks complicated, it is actually a straightforward computation if we remember that we just add and multiply elements in H like polynomials and keep in mind the relationships between the generators I, j and k. The ring H is called the ring of quaternions. To show that the quaternions are a division ring, we must be able to find an inverse for each non-zero element. Notice that a plus bi plus cj plus dk into A minus Bi minus Cj minus Dk equal to A square plus B square plus C square plus D square. These elements can be 0 only if A, B, C and D are all 0. So, if A plus Bi plus Cj plus Dk not equal to 0. A plus Bi plus Cj plus Dk into A minus Bi minus Cj minus Dk divided by A square plus B square plus C square plus D square equal to 1. Hence, H is non-commutative. If G is a non-commutative, then the group ring R of G is also non-commutative, which we will see in the next note. Considering a group G and a ring R. The group ring of G over R denoted by R of G is the set of mappings F from G to R with finite support, that is, taking a finite number of non-zero values. The addition of two elements F, G belongs to R of G is the mapping F plus G from x to F of x plus G of x. The product is the mapping F dot G from x to summation over uv equal to x F of u into G of v, that is equal to summation over u belongs to G F of u into G of u inverse x, which is well defined because F and G are a finite support. One can verify that R of G is indeed a ring. When G is a non-commutative group, R of G is a non-commutative ring as for R and S belongs to G such that R is not equal to SR. We have 1 RS not equal to 1 SR, where for G belongs to G, 1G belongs to R of G denotes the finite support function that maps G to 1 and all the other elements to 0. Now, we are in the end of the session. So, let us recall the concepts one again. First, we recall the concept of commutative ring with some examples. Moreover, we had seen about integral domains and fields. We had proved that Boolean ring is commutative. Also, we had discussed that the ring with unity has order p square is commutative. And then we moved to a non-commutative ring, and also we had discussed many examples like matrix and quaternions. Finally, we finished this session with group ring. I hope this content is useful for you. Thank you.